Now I know what you're thinking. Another flying car concept promising to be the future of airborne transportation. You've seen it a million times before, now where's the skip button? Well, hold on just a minute. Only a few decades ago, the idea of an all-electric car was considered just as unrealistic. But nowadays, it seems like they're everywhere. And it's only natural to expect the budding field of multirotor aircraft to grow just as rapidly. The next few decades will likely see a revolution in terms of personal transportation, the likes of which we haven't seen since the first mass-produced cars rolled off of early assembly lines and onto the unimproved dirt paths of yesterday. Dirt paths which were soon paved into the roads, streets, and highways of today. Along with this development of infrastructure, the guidelines and common courtesies gained from centuries of travel in horse-drawn carriages were adapted and modified through trial and error into today's traffic laws and regulations. With the recent advent of multirotor aircraft, there's an obvious question we need to ask ourselves. Is our current automotive-based culture ready for the next step? As the next technological leap in transportation appears on the horizon, are we really ready to take to the skies en masse as an aerial society? Now granted, we've been flying in aircraft for almost as long as we've been driving in cars. But is it really the best path forward to just hope that these two worlds will merge seamlessly together? To assume that the laws governing travel on the highway can even be combined with those governing travel in the air? To once again take our first steps into a new age, planning to simply duplicate existing systems and figure out the rest as we go? Or should we be a little bit more proactive in our anticipation of a near future where a significant portion of the population elects to take to the sky as opposed to the streets for their daily commute? I think the answer to all these questions is obvious. Luckily, this won't require new roads to be paved, bridges built, tunnels excavated, or the construction of hundreds of new airfields. But we will need to carefully consider the challenges inherent to an aerial society. Now, to really dig into those challenges adequately, we need to acknowledge the current state of aviation. For this video essay, I'll be focusing on aviation within the United States and correspondingly the FAA, or Federal Aviation Administration. Now, if we consider historic precedent for options to achieve a flying commute, we've traditionally had to choose between either fixed-wing aircraft or rotary-wing helicopters. And yes, I realize I will be excluding the more recreational forms of aviation for this analysis, such as gyrocopters, powered hang gliders, and paramotors, for example. Sure, those forms of aviation will get you in the air for your commute, but not at the same level of refinement or safety as the two primary contenders. For those of us who want to arrive in style, you'll need a hangar to store your aircraft, an airfield in both your backyard as well as at your destination, and extensive and expensive pilot training. In the recent decades, huge advancements in sensors, electric motors, and battery technology have led to the introduction of multirotor aircraft as a new option for personal flight. As opposed to generating lift through constant forward motion, spinning up a giant whirling gyroscope overhead, or strapping a big fan to your back and running through a field while dragging a parachute behind you, multirotors generate lift through a series of small, independently controlled propellers. Although initially introduced as small, remotely controlled hobby aircraft, the very same revolutions which have enabled electric vehicles to flourish can also be adapted towards full-size multirotor aircraft, like the Azura Personal Quadrotor. And you'll have to excuse the shameless plug. These technologies are rapidly converging on a day when a privately owned multirotor aircraft can be stored at home, fly directly to almost any destination, and park in a common automotive parking space. Granted, again, technology isn't there just yet, but in this case that's great news. We have a little bit of time to figure out the infrastructure demands of an airborne society before we fill the skies with daily swarms of mass-produced multirotor aircraft. So, having spent the last decade on and off designing a multirotor personal aircraft, while simultaneously considering the societal implications, let me take the first crack at how all of this could work. First things first, I have to admit I am an engineer. Identifying and solving problems are my strengths. Writing video essays or coming up with great names for new products? Not so much. So please bear with me as I try to muddle through this massive tangled web of thoughts, ideas, and concepts and string all of this into a single coherent narrative. Will it be the perfect end-all solution to the problem at hand? Probably not. But if nothing else, I hope it can act as a foundation to get more eyes on the problem and draw in more expertise. This is an ambitious challenge after all, and will require the skills, knowledge, and investment of many problem solvers to adequately overcome. But in my opinion, it's completely feasible and definitely past due. Now, before we dive in headfirst, it is important to dispense with a concept which has proven useful through the formative decades of aviation, but will prove deadly if not addressed for the needs of tomorrow. This would be what is known as the Big Sky Theory. This theory dictates that the probability of collision between two aircraft is unlikely simply because the sky is orders of magnitude larger than the little aircraft flying around in it. This theory is also so prevalent that it is used as a baseline to inform many of the navigational standards and guidelines for both commercial and recreational flight today. However, think about the last time you were stuck in traffic. How many white-knuckle near-miss incidents per day could we expect if every car miraculously transformed into an aircraft at the same instant? Every car levitates off the ground, climbs to a randomly selected altitude, and zooms off, taking a beeline to its destination of choice. And keep in mind, this is just the best case scenario, only considering the thousands of near-miss incidents we'd see in a single event. Every day, multiple times per day, an unprecedented swarm of aircraft would fill the sky. This is the default response from naysayers to dismiss whenever someone has the audacity to suggest such an outrageous concept as that of a flying car. But it does have merit if we only consider this introduction into the world of the status quo. Now, this shouldn't come as a surprise to anyone, but we can probably agree that new guidelines and regulations are needed to ensure a safe transition into an airborne society. Therefore, I'd like to propose an alternative to the Big Sky Theory, a new concept which I will be calling the Saturated Sky Doctrine until somebody comes up with a better name. As opposed to assuming there's plenty of sky for everyone, we now assume that the airspace will be saturated with aircraft to the extent that interactions between them are presumed to be common occurrences. Not to the extent that collisions are inevitable, mind you, just that flight in proximity with other aircraft is frequent. We can use this concept to generate some new guidelines in an effort to ensure a safe future flight environment. Also, since it's the 21st century, we can incorporate today's computing power from the get-go. In fact, multi-rotor aircraft are inherently computer controlled by nature. This is due to the challenge of balancing thrust and torque across a number of rotors to achieve control and stability. Although I'm sure someone will eventually, or already has, come up with an entirely human-controlled multirotor at some point, probably loaded with all kinds of mechanical logic that will achieve the same outcome. But for those of us who aren't from the 1920s golden age of aviation, we'll just let the computers do the heavy lifting. Also, there's no need to rewrite the bulk of today's aviation regulations to make room for the new kid on the block. But we will probably need a new classification for the low-flying commuter vehicles that these guidelines will govern. Again, I'm not great at naming things, so let's run with Multirotor Commuter Vehicles, or MCVs for now. Finally, the well-versed and astute among you will recognize some of the following proposals as being bold-faced, copied and pasted duplicates of pre-existing systems. In all honesty, there's almost nothing novel about the individual building blocks of what is about to be proposed, only that they haven't been put together into a single holistic approach yet. In the following discussions, I'll describe the purpose and function of each system at hand for the benefit of those who might be new to all of this. So, if you happen to be a subject matter expert on whatever system I am describing in this high-level executive summary, number 1, I already know I am glazing over a ton of detail. Number 2, this video is already going to be a lot longer than originally anticipated. And number 3, feel free to deliver your own deep dive into your area of expertise in the comments section below. We'll begin with laying out a highway system for our new aerial commuters. Luckily, we can leverage the ever-increasing capabilities of GPS to undertake the bulk of the heavy lifting. For redundancy's sake, we can also revive elements of the old decommissioned Earth-based low-RAN system, but I'll dive into that one later. Using GPS to determine and monitor the flight progress for the new MCV class will enable easy computation of flight parameters such as location, altitude, velocity, and vector, or direction of travel for the aviationally uninitiated. Now, the next obvious question would be, what would be the least offensive way to integrate a new class of aircraft into the same airspace currently occupied by the earlier mentioned helicopters and fixed-wing aircraft? Well, in general, MCVs will only need to operate at what is typically viewed as very low altitude, flying more or less map of the Earth from origin to destination. In aviation terms, the FAA generally regards this airspace as Class G, or uncontrolled. Once you've climbed high enough to clear any nearby obstacles, travel in any direction becomes feasible pretty rapidly, and there's no need to climb to 25,000 feet on your way over to the nearest grocery store. That being said, we'll also have to consider a minimum altitude so that we're not harassing people on the ground or blowing shingles off of the neighbor's roof. So let's begin with laying out this minimum nuisance barrier altitude. If you'll allow me to exercise my creativity in coining a term, I'll call it the floor. This would be the minimum safe altitude for MCV flight at full cruising speed. And the best way I can imagine this would be to lay a 200-foot thick blanket over the United States. It would bridge over mountains and valleys and generally smooth out rough terrain. This 200-foot minimum should be low enough to limit the amount of time spent climbing, while hopefully being far enough away from those on the ground to reduce disturbances to an acceptable minimum. Flight below this 200-foot floor would be restricted to low-speed hovering, maneuvering, and landing or taking off. Flight above the floor would be reserved for full-speed transit flight. 200 feet is also a really hard altitude to find a good reference object for, so it's roughly the height of the tablet held by the Statue of Liberty. We can take the elevation data from this blanket and save it as our baseline navigational map for the MCV compliant aircraft. We can then mark off certain areas which would be generally hazardous to MCV flight and exclude them from our map. Things like the Statue of Liberty, previously established restricted classes of airspace, government and military property, airport approach and departing lanes, highly populated areas, areas of historic significance, etc. Generally areas where flight is already restricted today, or where MCV travel might be particularly hazardous to the operator or to those on the ground. Beginning at the floor elevation, we'll add an additional 100-foot buffer layer for climbing and accelerating, or descending and decelerating to and from cruising speed. For example, an MCV climbing out would reach the floor at a low-speed hover and accelerate to full cruising speed by the time it ascends an additional 100 feet. So that would nail down a basic ground-to-floor maneuvering zone as well as a transition zone for high-speed flight. Next up is developing a directional lane system for our MCVs. Luckily, something like this already exists for commercial aviation. Directions of travel are split up amongst even and odd thousands of feet. This works fine for the big sky theory, but we'll need a more incremental breakup if we want to apply the saturated sky doctrine to an extremely compressed low-altitude band of airspace. Again, we only need to claim enough altitude for basic point-to-point flight while allowing space for maneuvering. And we also want to avoid intruding into airspace commonly used by the other forms of aviation. As previously established, the transition layer terminates at about 300 feet above the ground level and is used for speeding up and slowing down. We can now stack additional layers on top to account for the incremental directions of travel. My initial inclination would be for 8 layers in total, 4 cardinal directions, north, east, south, and west, and the 4 ordinal directions, for example, northeast and southwest. At the top of the transition layer, we'll set the first cruise layer as traveling north. The next layer above would intuitively be the northeast layer. Transferring from the first layer to the second would consist of an ascending right-hand turn and would see the MCV entering the second layer traveling northeast while maintaining cruise speed for the duration of the climbing turn. If we continue to set each individual layer height at 100 feet, again to remain close to the floor and maximize energy efficiency, then we can add up a 200-foot floor, 100-foot transition layer, and 8 cruise layers to put the total altitude claim for the MCVs at a minimum 1,200 feet above the ground for flat terrain, buffering to a slightly higher altitude in the case of hilly or uneven terrain. Just to note, this is considerably lower than the typical cruising altitudes seen by private aircraft, and meshes nicely with the FAA's already established guidelines for Class G airspace. As described, this system would work in purely 45-degree incremental lanes, although almost every flight would require at least one lane change in its flight path to reach the destination. However, to maximize flight efficiency, I think we can allow these lanes to be broken up into a smoothly transitioning climb. Let's say our destination lies somewhere between south and southwest relative to our origin point. Instead of flying in the southbound lane for the bulk of the journey, climbing to align with the southwest lane for the final leg, and descending back through the south lane lane to land at the destination, we'll just rely on a computer to interpolate the correct altitude between the two lanes for the entirety of the flight. Since all MCV traffic following this lane strategy would be flying in roughly the same direction within each lane, the chance of a head-on or high-angle collision is significantly reduced. Adherence to this slightly relaxed cruise layer system would see an MCV entering the first layer at cruising speed traveling north, followed by an ascending right-hand turn until the correct altitude is reached. However, the realist in me knows that, number 1, people are lazy, number 2, will want to get on their way as quickly as possible, and number 3, won't want to waste time spiraling up and down at the beginning and end of each trip. So we can further improve flight efficiency by bending the rules in an additional way. As opposed to the whole spiraling up and down business, I would anticipate the typical journey would consist of traveling in the desired direction for the entirety of the flight, and simply climbing to the correct altitude with respect to the lane system. If a direction change were necessary mid-flight, only then would I anticipate a corresponding spiraling turn. The likely realization of these guidelines being that the cruise layer system I've described so far only determines the altitude for the desired direction of travel, not the process to achieve it. While this system seems like it would be difficult to manage for what I expect to be minimally trained MCV operators, keep in mind that this class of aircraft will be, by definition, computer controlled. You'll have noticed by now that I hesitate to refer to this theoretical MCV operator as a pilot. The term pilot carries a connotation of direct control over the aircraft, and a responsibility for compliance with regulations, safety, navigation, etc. The requisite skill and level of training required to achieve this title also acts as an unfortunate barrier to entry for the bulk of the population. In order to reduce this initial hurdle, I think we can use the computer-controlled nature of multirotor aircraft, and MCVs in particular, to our advantage. I'll make an analogy to the relationship between the typical driver and a GPS navigation system. The GPS tells the driver where to turn, and it's the driver's responsibility to ensure that they safely operate their vehicle, obey traffic laws, and avoid obstacles and other vehicles while negotiating the specified turn. In the case of an MCV, these roles will be reversed. The operator tells the MCV where they'd like to go, and the onboard flight control computer determines whether the aircraft can safely and legally comply with the request before executing the maneuver. I think of it as computer-assisted flight, or in other words, the MCV operator controls the aircraft through an autopilot at all times. Which makes this computer-assisted approach a crucial element to the MCV classification, and leads us nicely into the Automatic Collision Avoidance System, otherwise known as ACAS. While a substantial portion of this discussion has been directed towards the use of MCVs as commuter vehicles, it's even in the name after all, we cannot ignore that a significant number of flights will be taken simply as joyrides. I've already acknowledged how unlikely it is that operators would strictly adhere to the lane system while on their commute, and it's even more unlikely that they'll want to follow the system while enjoying a flight over scenic terrain during a picturesque sunset. Traditionally, collision avoidance is handled by a mix of pilot vigilance, air traffic control, and an aircraft's own radar system. However, it should be obvious that bombarding the skies with thousands of high-power radio signals would be detrimental to society, and we've all seen enough examples of other drivers to know that some drivers could use a little bit more training and vigilance before getting behind the wheel again. And finally, it should be obvious that expecting a human-based traffic control system to manage a massive influx of aircraft would also be a non-starter. Simply watch cars enter and exit a highway while imagining a poor soul highway traffic controller trying to choreograph the maneuvers, and you'll see the issue here. Further, we can't give everyone radios and ask them to hash things out in the sky. Can you imagine the road rage that would ensue if every driver were given the means to insult and slander each other's heritage as they race down the highway? And we only need to spend a few minutes listening to recorded ATC communications to know that that is a traffic control system that we want to avoid in its entirety. I would suggest the Real ATC and VAS Aviation channels as a couple of really good examples for these kinds of recordings. Even if you're still skeptical about everything I've laid out so far, it won't take long to come to the same conclusion that I have, that we need a completely different, self-contained approach to traffic management for a saturated skies environment. So here's my proposal. Let's imagine the function of radar as a computerized game of Marco Polo. In other terms, the radar asks, "Where is everyone?" or the equivalent of shouting, "Marco," which is followed by a series of Polo replies. The radar collects the direction and time delay for each reply and calculates the position of the other aircraft. Now let's change that call and response system to a much simpler "I am here and I'm doing this" announcement. Current commercial aircraft already use a system like this in conjunction with their onboard radars, conveniently also known as ACAS. As we've already determined, each MCV will know its precise location, altitude, speed, and heading through its own flight management computer. So we'll just broadcast this information to all surrounding aircraft. And in return, they'll tell our MCV where they are, and everyone can just track each other's flight paths. We can either copy existing protocols for this communication or develop our own, as long as we can ensure that all relevant information is broadcast in a standardized format. Things like aircraft identification, flight data, and operational status. For example, whether the MCV is operating normally or in an emergency situation. Finally, we can avoid overlapping each other's broadcasts by including a randomized time delay until the next broadcast in each transmission. Other aircraft could then time their own broadcasts for an available period of airtime. These items would be repeatedly broadcast every 1 to 2 seconds and would represent a very small amount of radio traffic, especially in comparison to sending, receiving, and decoding radar signals. The individual MCV flight control computer would then track nearby aircraft and calculate the minimum merge distances and time to merge relative to its own flight path. If this distance is determined to fall below a certain safety threshold, a course deviation could be input by the flight controller and automatically acted on. Similarly, one would expect the computer to actively ignore commands which would result in an unsafe merge, and the extent of these course deviations would be determined by the severity of the impending merge. A typical avoidance maneuver might not even be perceived by the operator, although an alerting tone would likely notify them anyways. In an extreme case, the MCV could execute a maneuver impossible for fixed-wing flight and come to a mid-air hover to avoid a collision. Further, if we assume both aircraft in this example are MCVs, then both aircraft would react to the impending unsafe merge with their own avoidance maneuvers. And even if the ACAS were malfunctioning in one of the MCVs, the built-in redundancy of the system would allow the other aircraft to avoid the incident entirely on its own. We can further rely on computing power to calculate second, third, and even fourth order interactions of the surrounding aircraft. For example, if two other aircraft nearby are on a close merge flight path, and the necessary directional change of one or both of them would result in a new unsafe merge distance with your own MCV, then your MCV would proactively move out of the way to ensure the other two aircraft had room to avoid their own impending incident. I'm specifically thinking of an aerial version of that car entrapment insurance scheme that we hear about every once in a while. The one where 3 or more cars box in the victim car and cause a fender bender so they can collect on insurance money. We would want to avoid such behavior in the sky. This system could also be expanded to the current forms of aviation, which would further smooth the integration of the new MCV class. I envision a small, easy-to-install add-on transmitter. It would only need power and initial programming, and would broadcast flight data to the surrounding aircraft in the same way as an MCV. Although it wouldn't be integrated to the extent that it could take over an aircraft and avoid an incident all on its own, this system could still alert the pilot of an impending unsafe merge with another aircraft. It would also function in a way to move MCV traffic out of its path, in a manner similar to the malfunctioning ACAS example mentioned before. In this example, the flight status element of the broadcast might be changed to something identifying the aircraft as a human-piloted aircraft, and an MCV's avoidance maneuvers might reflect a greater urgency in this case. So there's a lot to be digested in what I've covered so far, but let's fold in some of these navigational and traffic avoidance systems together to further flesh out this new flight environment. It's highly likely that we'll need to make sporadic changes to the flight map established earlier. Things like temporary no-fly zones, new public landing pads, recharging stations, etc. For example, maybe there's an accident or natural disaster and the skies need to be cleared for emergency response aircraft. Or maybe a public event is planned and it would be dangerous or or undesirable to allow aerial traffic overhead. This is where we can supplement the GPS-derived navigation system with an additional ground-based beacon system. Let's say a new 1,000-foot radio tower is erected. We certainly don't want MCVs slamming into it at full transit speed, and we definitely don't want to force every MCV operator to download a new several gigabit flight map every day before they take out their new shiny Azura for a spin. So we create a beacon system which can be used to demark new or temporary changes to the flight map. These beacon transmissions would be monitored by the MCV flight controller in the same way as the proposed ACAS transmissions. Similarly, if a business were to add a new public landing zone or MCV-specific infrastructure, a beacon could be installed to identify the new feature to the flight controller. These attract and denial beacons would be used to adjust flight behavior on the fly, in the same way that signs and traffic cones are used to change driving patterns. Landing zone beacons would also incorporate their own version of a digital air traffic control, in that they would manage incoming and outgoing traffic, assign holding positions, the order of arriving and departing aircraft, etc. The signals from these beacons would be processed by the flight controller and would appear as overlays on the MCV's navigation screen. Integrating the computer-assisted flight controller would further ensure automatic compliance with temporary restrictions. A subroutine similar to the ACAS system would automatically deviate course when approaching a no-fly zone, and the navigation system would intuitively plan its flight path around them. Further, these beacons could act as a sort of backup navigation system if the MCV is struggling to receive GPS signals. Since the beacons are stationary in known locations on the ground, or at least I can't imagine any reason they wouldn't be, an MCV could triangulate its position using these signals. I mentioned the old decommissioned LORAN system earlier. This is basically what it was. If nothing else, the ground-based beacon system presents an opportunity for redundancy in terms of navigation systems. And as a final note, these types of beacons would need to be heavily regulated by local governments. Making changes to the navigational map through the placement of no-fly zones, temporary or otherwise, would require first studying the resulting impact on flight behaviors to ensure that traffic is not unreasonably impeded or safety compromised. An easy example to imagine would be funneling of traffic into a tight corridor between denial zones. Regarding attract-type beacons, an equally strict review in terms of traffic and safety would also apply. Businesses would have to apply for a permit to install a beacon, and the services provided would need to meet certain standards for MCV access. Another easy example being the landing zone cannot be surrounded by power lines or overhanging trees. Which brings us to the unfortunate part of this discussion, the necessity for government oversight. We're entering the murky area of jurisdictions, licensing, training requirements, and above all, bureaucracy. One of the biggest benefits of the MCV concept is the significant improvement in efficiency regarding personal travel. As we've already established, the MCV classification will be comprised of low-flying, short-range, highly automated aircraft, all taking off and landing at random, mostly non-airfield locations. However, the FAA traditionally likes to exercise its authority over where and how aircraft are operated. Even though there's an appropriately sized empty plot of well-mowed grass next to your favorite Chick-fil-A, the FAA is probably not going to be too thrilled to hear you decided that a helicopter was the best way to get your spicy deluxe with pepper jack cheese, extra buffalo sauce, fries, sweet tea, and a yogurt parfait with granola. Unfortunately for the MCV class, this functionality is a primary design objective. Luckily, this subject has already begun to be addressed by another similar budding field: automated aerial taxi services, which have gained a lot of attention recently. Now, if you'll allow me to make another association, it wouldn't be too much of a stretch to lump the proposed MCV classification into the same boat as an automated aerial taxi. As I've already established, the true pilot of an MCV is the flight control computer, which is the same in an automated taxi. Although I can't imagine why anyone would prefer calling a taxi over owning your own aircraft. In either case, the taxi customer or MCV operator is really more of an active passenger, if you will. And if this aerial taxi service happens to also allow changes to the flight path mid-flight, then there really isn't a difference between the two. On the flip side, if the FAA determines that all MCV operators need to be fully licensed and certified pilots, then wouldn't this same standard be held for a passenger using an automated taxi? If you'll allow another proposal of an optimum solution, a new highly simplified pilot classification and license type rating is going to be needed to allow for the operation of the types of computer-aided aircraft that we'll be seeing more and more of. Considering the dual nature of the MCV concept, half ground vehicle, half aircraft, in actuality we're probably looking at governmental oversight being accomplished through a perfect mix of the cranky old men at the FAA in combination with the cranky old ladies at the DMV. First, it's highly unlikely that the FAA is going to relinquish jurisdiction over any airspace. Secondly, integration into any pre-existing automotive infrastructure or the use of public roads will necessitate buy-in from state authorities. In reality, splitting oversight between these two entities might not be too hard to set up after all. The FAA can manage oversight for the navigational map, the beacon system, integration with existing forms of aviation, requirements, certification, etc. Pretty much what they do nowadays for aircraft. And each state's DMV can handle training, registration, titling, law enforcement, and compliance, etc. Pretty much the same stuff as they do nowadays for motor vehicles. So, in an informal, hopefully temporary conclusion, the goal here is to start getting other minds thinking about these challenges. There really is very little in a technological sense standing in our way to achieving this idealistic utopia of personal flight. It's right around the corner, but we need to develop a foundation in earnest before it gets here. Not only do we need to address the infrastructure and regulatory needs of an aerial society, we also have to change our perception around the idea of a flying car. Airborne versions of the daily commute to work, scenic joyrides, and quick hops to the store are things that we have yet to truly wrap our minds around. If you've gotten this far, I'd like to thank you for taking the time to hear me out on these rambling thoughts and solutions, and I will be posting more as time goes on and the project moves forward. I hope in the meantime that this first discussion will act as a foundation for your own consideration on this challenge, and I really look forward to all the different insights and perspectives that you all can bring to the table. Finally, let's work together to develop this concept into a fully detailed vision for the future. Until next time, take care.